Alright, my name is Massatelli, and today I'll be talking about the effects of different microalgal feeds and their influence on larval development of the sea urchin Trypanostis gratilla. Just a little bit of background information. If you've ever been to a Japanese restaurant, you've probably seen uni on the menu. Uni is sea urchin roe. It's regarded as a premium seafood product, especially in parts of Asia like Japan and European countries such as France and Denmark. The popularity of uni has caused a massive decline in the sea urchin population due to overfishing. And this has put pressure on commercial fisheries to produce species of urchins that are good for aquaculture. Only problem with commercial sea urchin rearing is that husbandry during the larval stage is extremely intensive. Every parameter, light, temperature, pH, feed type, quality, quantity, all have drastic effects on the outcome and survival rate of sea urchin larvae, which is already very low, at around 17% on average. So the species that we're going to be looking at today is Trypanostis gratilla, also known as the white-spined sea urchin, and it's also known as a collector urchin. And it gets that name because it will find bits of coral and rock from the reef and actually put it on the top of its test to camouflage itself from predators. They're found in just about every ocean around the globe, except for the Arctic and Antarctic Ocean. They're found in around 2 to 30 meters of water. They range in size from about a quarter all the way up to a baseball or a large or a softball. So the development cycle of a sea urchin is very complicated. When the eggs are first fertilized and they turn into a two-arm plutei larval stage, and that form is pelagic, which means that it's free swimming and it drifts with the currents. There are 4 different stages of development. There's a 2-age plutei stage, there's a 4-arm larva stage, and then there's an 8-arm echinoplutei stage, and then the adult sea urchin after that. And the arms of each of these larval stages has a direct correlation to feeding activity. The longer the arms, the more feeding that the urchin can undergo. So a common practice in the study of larval development of sea urchins is to measure the ciliated band length on the post-oral arms to assess the response to a particular diet or rearing condition. So my question was, what's the optimum feed for these urchins, T. gratilla, and what are the specific phenotype plasticity associated in response to the change in feed type? So we're looking at, does feed type affect the size of the urchin, or does it affect any other parameters that might cause an economic favorability to this particular species and that particular species of feed? So adult T. gratilla were collected off the coast of South Africa in September of 2008. They were spawned artificially by an injection of potassium chloride into the gonads through the test, and the eggs and sperm were collected. They were then combined in a petri dish at a ratio of 100 sperm to 1 egg to induce fertilization. After 2 days, the fertilized eggs were all checked, and once they entered the pluteus 2-arm larval stage, the experiment began. So they entered them into experimental conditions. They were reared in 12 100-liter cylinders with a complicated fresh seawater system and filter system, and they stocked the tanks at a density of around 5 larvae per milliliter. So they did 2 trials, one in May and one in September, and that's just because they didn't have enough room to do everything at once, and they wanted to have a large enough sample size. So in the first round, they had Isochirus, P. lutheri, and C. muelleri. In the second round, they also had C. muelleri, but they added Pseudocastatum and T. swastika. So the reason that they had C. muelleri in both trials is because it's shown to be the best feed until competence in commercial rearing of urchins. And they wanted to have a control between both of the experiments, both in May and September, so that they could later plug it into an equation and compare all the feeds together. So they started out at 4,000 cells per larva, and they had 8-hour feeding cycles. So every 24 hours, they had 8 hours, and they turned the pumps off. They introduced the algal cells for 8 hours, and then after those 8 hours, the tanks, the filter systems were immediately turned back on to get rid of all the uneaten food. When the larvae reached the kind of plutei 8-arm stage, they actually increased the algal cell concentration during feeding to 10,000 algal cells. They recorded the growth and development of the larva every 2 days. So they measured a couple of things. The first, they measured survival, and they took density samples of the larva. So they took 3 15 milliliter samples, and then from those 15 milliliters, they took 3 milliliters, and they placed them on a Bogorov tray, which makes it easy to count, and they put that under a dissecting microscope to count the density of the urchins. And then they looked at morphological differences to determine age rather than size, because an increase in feed can increase the size of an urchin, but not necessarily make it age faster. Development and size of the urchin are generally not linked. So they sorted them into 5 developmental stages characteristic of a majority of larvae. They had the 2-arm plutei stage, they had an early 4-arm stage, an advanced 4-arm stage, an early 8-arm stage, and an advanced 8-arm stage. So this is a picture of a 4-arm plutei larva, and the 2 arrows show the ciliated band that is measured when they're looking at the post-oral arm length. And this is common in many sea urchin experiments to determine the development of a sea urchin in response to certain stimuli. So the statistics use, they use the nested ANOVA on the body profile, so the post-oral arm length, and they nested feed within tank to account for intertank variation. The survival was assessed using a linear regression analysis. So the result, the larva fed Isochirus had the highest survival rate amongst feeds with a 13.8 survival rate. In regards to development rates, the fastest development was found to be in the C. mulleri treatment, specifically the May C. mulleri treatment. P. lutheri did not develop past the 4-arm stage in the main trial, but they still had a decent survival rate. So here are the results of the post-oral arm length and other body parameters on the left-hand graph. So up at the top is the post-oral arm length, and that's what they're looking at mainly in this study. These are other body metrics that they used to determine growth, but it's most common to use the post-oral arm length. So over here is May, and over here is September, and then they took both of these graphs and they entered the data into what's called a von Bertalanffy growth model, and that combines the data so that it's all on one graph, which is over here on the right. And so on the y-axis, you have the post-oral arm length in micrometers, and then the day is on the x-axis. So looking at the graph, C. mulleri with the small dots and the big squares has the highest or the fastest growth rate, and it's also up there is Isochirus. Getting down to the other strains, we see a much lower growth rate. So this is a 100% graph, and this shows the development stages, the amount of larvae in each development stage as the experiment progresses. So on the x-axis we have the day, and on the y-axis is the percent in each stage. So looking at this graph, one thing to notice is down here, T. swastika actually didn't develop past day 8. All of the larvae died. When looking up here at C. muelleri, on day 16, all of the larvae were generally in the 8-arm advanced stage or adults by then. So when you're looking at this graph, you're looking for a fast trend downward with the colors. That indicates fast development. And when you're commercially rearing urchins, that's what you want. You want fast development. You want to get these guys out of the larval rearing stage as quickly as possible. So here is the graph on showing the survival rates of the urchins. And on the top is the May, and on the bottom is September. And one of the things to note is that during the September trial, after 2 days after they put the larva into rearing conditions, they actually had a steep drop-off, which you can see here. But after the drop-off, the rates kind of leveled out to match the May trial. And with this, Isochirus actually turned out to have the highest survival rate, despite not having the fastest development rate. So conclusions, feed type is extremely important for the development of T. gratilla. So we saw differences in some feeds managing to reach competence within 16 days, and then some feeds where all the larvae actually die by day 9. So larvae fed C. muelleri, S. pseudocastatum, and Isochirus all managed to reach competence within 22 days, which is very good. Pseudocastatum and Isochirus have been shown in other papers as common feeds for urchin larval rearing, either individually or combined. And C. muelleri has been shown to provide exceptional nutritional value to T. gratilla. So in the future, one thing that I would like to look at is looking at combinations of microalgal diets and benefits and detriments to a commercial rearing operation. So it may be that a combination of 2 different microalgal diets may cause development to shoot, and it also may increase survivability. Because like with Isochirus, you had high survivability but slow development, and C. muelleri, you had lower survival but higher development. So what happens if you mix the 2 together? Another thing to look at would be looking at the economic impact of finding new species that are suitable for aquaculture. Aquaculture is very hard, and the survivability of the larva is so low that many species of urchins just aren't suitable. You don't get high enough yield. So finding other species like T. gratilla to supply the industry would be a good direction to go. All right, thank you for listening. Are there any questions?